Okay, we're going to try to keep going on this. So they want you to sketch both the line and the reciprocal to make a point. So that's a positive line. It's going to go through the point. The x-intercept is going to be when 2x minus 5 is equal to 0, which is clearly going to be equal to 5. And then when you divide both sides by 2, when x is 5.2 or 2.5. So it's clearly going to go through this point, 2.5, comma 0. It's also clear because it's a plus 2 slope that the left side, it's going to be upward, rising like that. And go through. Now the connection with this is the 1 over. The restriction here is going to be the same as that, which means the asymptote in purple. Let's try that asymptote again. Is going to be the same as the x-intercept, but because 1 over a positive number is still a positive number, everything on this side is going to be the positive, and everything on this side is going to be the negative. And you can figure it out also by putting in like a 0 for x here, and it becomes 1 over minus 5, which is negative 1 over 5. So it's clear that over here it's 0, it's hugging the y-intercept. Another thing to point out that when there's a 1 up here, the horizontal asymptote is always y is equal to 0. Even when there's an x up here, if there's 2x squared, like if there's x over x squared, or even x squared over x cubed, whenever the x up here is smaller than the x power down here, y is equal to 0 is the horizontal asymptote, which means you're going to have this connection. Whenever you want to see when it's negative, because there's just one x down at the bottom, it's always going to follow a similar pattern as the parent graph. Wherever you want to see to confirm if it's positive, just pick a value that's to the right of the asymptote, like 3. So 3 over here becomes 1 over 6 minus 1, minus 5 rather, which becomes 1 over 1, which is 1, positive 1. So clearly over at 3, that's going to be one of the main dots. And it's often where when it crosses through the line like that, it's when the x value is equal to the y value. So we should see a minus 1 comma 2 over here. Sorry, a 1 comma minus 2 plus 1 comma minus 2 as a dot over here. And we'll see. So the best thing to do is just always use your decimals. So here's the line. Oh, it's minus 5, sorry. And let's just make that f of x, and that way we can just let decimals draw it for us. And there you go. And let's see, there's the 3 comma 1. And let's see the relationship to the line there. It's 3 comma, oh yeah, okay, 3 comma 1. Yeah, it's when the y value is going to be the same as the numerator, actually. Is when that's going to occur, and 2 comma minus 1. So when we see it, there are those 2 points. Which makes sense, because 1 over 1 and 1 over minus 1 won't change it. And here's the asymptote. Oh, x is equal to, and of course the horizontal, y is equal to 0. We'll make the asymptotes green. There you go. And because it's just 1x at the numerator, 1x to the power of 1, you'll always have this pattern. Sometimes they'll switch. For instance, if it's a negative, they'll switch quadrants. But it's very easy to figure out which quadrant they are, and once you do, you can pretty much say, as it approaches the asymptote on this side, it's going to approach positive y infinity. As it approaches the asymptote on this side, it's going to approach 0 from the positive side. And as we approach negative infinity, we approach 0 from the negative side. See that the y values are all negative, but almost 0. And as we approach the asymptote, we'll always approach y negative infinity. This will hold true for any time that there's just one x value in the denominator. Let's look at the next one to see. This is also a line with a positive slope, but it's going to go through a negative. It's going to go through a negative point, and it's when 3x minus plus 4. This is the y-intercept. It's equal to 0. To get 3x is equal to minus 4. Divide both sides by 3. When its x is negative 1.3333. So on the line we'd have a y-intercept, x-intercept of this. And because the slope is 3, it's going to be a positive graph like that, which means the corresponding 1 over graph, which is this one, the asymptote cannot be negative 1.3. So if I do the asymptote in red, the asymptote will share the same line as the x-intercept. We can see that this side of the line is positive, so 1 over it will be positive, so we can quite certainly say it's going to be like that. And let's just see it. 3x plus 4. You should use Desmos for most of this because after a while it gets tiresome drawing it. So x is equal to negative 4 over 3. There we go. And we can see the graph. And there's the red line. 3x plus 4. Yeah, and you can see it's going through the asymptote there. That's the y-axis over here at negative 1.333. So I think they want to show you the connection between the x-intercept and the asymptote. Then they want you to do it over and over and over again. So a lot of this I'm just going to let Desmos do it, but I'll just go through it. Factor this first. It's clearly x plus 2. Know your factors. That helps a lot. That means the reciprocal would be this. Notice that there's 2 x values down there. We're going to have 2 x-intercepts, and the question is, when will this be positive and when will it be negative? And the x-intercepts are x is equal to 2 and x is equal to negative 1, negative 2 rather. What kind of graph is this? This is a upward facing parabola. It goes through negative 2 comma 0 and 2 comma 0. So it's safe to say that the vertex of it will be right between those 2 points. So if it goes through negative 2 comma 0 and 2 comma 0, halfway between that will be 0. So we're going to find the vertex at 0 comma something. When I put 0 in here, I get minus 4. Safe to say that the vertex of this will be at 0 comma minus 4. That's because vertexes are always halfway between 2 points on the same y-axis, the same y value. And the big question is, ask yourself, when is this parabola in negative y values and when is it in positive? What's clear on every side, keep in mind it's going through this, so if I'm going to draw it properly, it really looks like this. There we go. And it's clear that it's negative between the 2 x-intercepts and it's positive over here, which means 1 over that will be the same case. So we can safely say, if I draw it in green, this will be one value asymptote, this will be another. One side of the graph is going to look like this. Like that. The other is going to look like that on the other positive area. Like that. And this side's going to look like this. But if you're unsure, take any value to the right of this asymptote and to the left of this asymptote to see where the graph falls. A good value is 0. So when we put 0 down here, we get 0 plus 2 and 0 minus 2, which just becomes plus 2 times minus 2. We get negative 1 over 4. So that means at 0, it's going to hug the y-axis. You can even take a value that's just to the right of negative 2, like negative 1. Negative 1 here makes positive 1, and negative 1 makes negative 3. So we get negative 1 over 3. We can see it's starting to go down. And if you take a value that's just to the right of this asymptote, like negative 1.999, you're going to discover y is approaching negative infinity. Same when if you take 1.99. But as soon as you take a value to the left of this asymptote, let's say negative 3, well, negative 3 plus 2 is negative 1. And negative 3 minus 2 is negative 5. Negative 1 times negative 5 becomes plus 1 over 5. Which means it's going to hug it and go up. And then if you take a value to the right, like 3, 3 plus 2 is 5. 3 minus 2 is 1. 5 times 1 is plus 5. Plus 1 over 5. But let's let the graph speak for us. So we're going to do x squared minus 4. There we go. And we're going to do x is equal to 2, x is equal to minus 2. And we'll make them both green. Yeah, green. There we go. I'm going to turn off the parabola. Sure enough, there are the values as expected. And again, because it's 1 over, 1 is the numerator, we'll never have an x-intercept with 1 over the numerator, which means we're always going to be on one side of the y horizontal asymptote and on the other. Okay, let's look at the next one. Next one is B, another parabola. This time, where's the vertex of this parabola? Where's the vertex of this parabola? Because they give it in vertex format. Okay, well the vertex is clearly at 2, negative 3. Is that positive or negative? That's in the negative y values. Is this parabola facing up or facing down? It's facing up. So that means down here, sorry, at 2, negative 3, this is where we'll find the vertex, and it's going to go something like that. Finding these is easy. You just set this to equal to 0. Okay. So let's do it on a different line here. So add 3 to both sides. And this means squared. Square root both sides is equal to the square root of 3. And by the way, when you square root both sides, we now have to add a plus. And x minus 2 is also equal to a minus version of it. And we solve for each individually. We simply add 2 to this, and we subtract 2 from this. So these will be our x-intercepts, but they will also be our asymptotes. And what is square root of 3 plus 2? Square root of this plus 2. Let's put it in memory. So plus 2 will be about 3.73, and minus 2 will be negative 0.266. 26 something. Let's see if that's true. So we get x minus 2 and x minus 3. Squared minus 3. And let's put our asymptotes at x is equal to the square root of 3 plus 2 and square root of 3 minus 2. Alright, let's see what happened there. Over x squared minus 2. Oh no, they're both plus 2, just one's negative, sorry. That's going to be plus 2. And this one's just going to be negative. There we go. Got the correct asymptotes in there. And let's throw in the actual parabola. Okay, notice the connection. When the parabola is negative, my inverse is negative. When the parabola is positive, the inverse graph is positive. And also notice the crossover point represents the asymptote, because 1 over these y values would produce an impossible result. So that they're just showing you the connection between the two graphs. If you wanted to see where your graph was positive and negative, you would instinctively know it's going to go negative, positive, negative once you understand the parabola. But if you don't, you can just take a value that's to the left of this asymptote, which would be, let's see, it would be, let's say 0. So if we take 0 and we put it in here, and we just find g of 0, let's say. We discover it's negative. Oh, sorry, I had an x in here. We discover it's negative. Oh, I forgot the squared, sorry. There we go, we discover it's positive, which makes sense. Notice if I take a value that's right near the asymptote, which is like 0.2599999, or 2549999, we approach infinity y. And if I just go to the right of it, like 0.27, I approach negative infinity y. That's on either side of the asymptote. And you can just confirm, like g of 4 is positive, therefore the graph, all the graph on that side will be positive. And that's because it can't cross the x-axis, so wherever you find it's positive to the one side of an asymptote, it will stay there as long as this numerator is 1, because there's no way to create a 0 when the numerator is 1. Think about that a bit. There's no x value to put in here where the result of this would be 0. Okay, let's move on to another one. This one is also parabola, and I think they're just getting you used to figuring out the pattern. What do we know about this parabola? Well, we only know one thing. It goes through 0, 2, but that doesn't mean it's... We also know it's upward facing. And if you wanted to get an idea of where the vertex is, it's negative b. So what's b? It's negative 3. So what's negative 3? What's negative 3? Positive 3 divided by 2a. What's a? 1. So we're going to find the vertex at 3, 2, which is 1.5. And because it's, I don't know what its y value is there, but that doesn't matter. Actually it does. So if we put 1.5 in there, let's see what we get. 1.5 squared minus 4.5 plus 2. Yeah, it's just barely negative. So we're going to have a little spot here, just a little spot, where this graph goes down and just touches negativity and then goes up, which means in the asymptote, the reciprocal, the asymptotes will be there like this and be there like that. Let's see if that's true. Let's look at x squared minus 3x plus 2. Let's turn it on, turn this off. Okay, and we're going to turn off all these other ones too. And we're going to just put f of x in here, like that. Before I figure out these values here, I can always make my x equal, or I can always make x squared minus 3. I can always ask when is f of x equal to 0 to find my asymptotes. And it should draw them. When is f of x equal to 0? I'm surprised it didn't draw them. Don't know why it didn't accept that. Try it again. For some reason it's not accepting it. Let's see. Oh, I see. I can't make it f of x is equal to 0 like that. I can do the formula equal to 0. There we go, and it'll draw the asymptotes. Notice it it's essentially drawing the x-intercept for this. Now let's turn on the graph. Yeah, there we go. And you might say, well, how would I figure out where to graph this exactly? You can always kind of take a middle point between the two. What you discover are the x-intercepts 1 and 2. You can try to find g of 1.5, and you can see that it peaks out at about -4. It'll always have a symmetry when it's 1 over things. And if it's a parabola as the denominator, you're going to have 2 asymptotes. If it's a cubic as the denominator, you're going to have 3 asymptotes. If it's a line as the denominator, you're going to have 1 asymptote. And the whole point of this is to see these patterns. I'm just going to put the rest of it in here. That's going to be an upward facing parabola where the vertex is -3, 0, so it touches. And that's a good question. I believe what will happen when it just touches 0? I believe it's going to create a thing like this on either side. So let's have a look at that. X plus 3 squared. And we'll make this equal to 0. There we go. Sure enough, there's only one possible asymptote, and that's when x is -3, because there's only one solution to this, and that's when x is -3, so you get this weird situation. And if we were to look at the original graph, the reason is because it just touches the x-axis. So it's going to create this situation where there's no possible values that can be in the denominator. There's no possible values that are negative here, so you're never going to see any inverse of the graph in the negative area. This is kind of a roundabout way of studying 1 over rational graphs. I would just do it another way. This is another one that's upward facing where the vertex is clearly 0, 2. So it's never going to be in a negative zone. And let's see, and I don't believe there's an asymptote possible. So I believe what we're going to see is this weird thing where it goes up to a peak and then comes down. It's going to have a weird bump. Let's see if that's true. Let's have a look at it again. X squared plus 2. Yeah, there's the weird bump that's going to happen at 0. And that's just, if you study the original graph, there's never a negative in here. And it never touches the x-intercept, so you're never going to have an asymptote. But the inverse will produce these things that hug the horizontal asymptote, y is equal to 0. And it will produce a max value there where the vertex is, and then it'll go back to hugging. It's because if you plug in some values here, like let's say 1 over a million, you're going to get a almost 0. If you plug in 1 over negative a million, you're going to negative something very small. Actually, no, for x squared, it's going to become positive again, plus 2. So no matter what you put in the denominator here, it's going to come out positive. Just the bigger you put in here, the smaller y gets, because it's 1 over. And the biggest possible moment of y is when x is 0, and it becomes 1 over 2. That's why the highest point we have here is 0, 0.5. Better just to fool around with the graphs and understand the connections. So this last one here, it's downward facing, and its vertex is -4, +1. So we'll have a bit of a positive area here. So in this case, we're going to have a graph that looks like this. We're going to have an asymptote that we'd have to solve. We'd have to figure out where it hits 0. And we'll do that. Actually, we'll do that right now. When is this equal to 0? Well, we set it to 0. And we do reverse story. First thing, we subtract 1 from both sides. Then notice that the bracket's being multiplied by -1. So when we divide both sides by -1, we get this. Then when we take a square root of both sides, the possible answers are x plus 4 is equal to +1, and x plus 4 is equal to -1. When I solve -1, I subtract 4 from both sides. I get x is equal to -5. When I solve this one, I get x1 minus 4. I get x is equal to -3. That means that's going to be the x-intercepts, but it's also going to be my asymptotes. So you're going to have two asymptotes here. The first one at x is equal to -5, and the next one at x is equal to -3. And because this is a downward facing parabola that looks like this, there we go. Now let's put it in the right spot like that, and goes through the x-intercepts there. You are going to have a positive in this zone. So you're going to have a drawing that looks like this in this zone. And in these zones, you're going to have things that hug like that. And to find this middle lowest point here, what's the middle point between -3 and -5? It's -4. Put -4 into our equation right here. When I put -4 in for x, I get -4 plus 4, which creates a 0, so this whole thing becomes 0. And I'm left with 1, but remember it's 1 over 1. And let's see. Oh yeah, it's going to be -0, which shouldn't matter, 1 over 1. So that means this point right here will be -4, 1. So you can find the midpoint there. Let's see if that's true. So we're dealing with -x plus 4 plus 1. Okay, we'll just turn this one off. There it is over there. Let's put in our two asymptotes. There's our two asymptotes. Let's make them both green. And let's make our g of x equal to 1 over f of x. And there we go, and let's check the point. If we found the right point, yeah, -4, 1. And then all the other behavior is normal. It's going to hug an asymptote, reach the lowest value, and then hug the asymptote. Over here, it's going to hug the asymptote, then hug the horizontal asymptote, hug the asymptote, then hug the horizontal asymptote. You can see that pattern over and over again. So I think they was just exploring 1 over parabolas. For each function, determine the domain and range, positive and negative intervals, increasing, decreasing intervals, and then find out the same for the reciprocal. So this is a line, this is a line, this is a parabola, this is a parabola. Bit of a pain. Much of the same thing. I would just strongly recommend just put it into Desmos instead. Right? But just very quickly. The first line set to 0. X will be equal to -4, which means that will be the asymptote of it. And for the other one set to 0, x is equal to -3 over 4. One has a negative slope, one has a positive slope. There's the positive slope, which means the graph of the line would look like this, and it would go through -4 over here, which means if I was to draw the reciprocal, it would look like that. And wherever the line was positive, wherever the line was positive, the graph would be positive. And wherever the line was negative, the graph would be negative. So that would be this first one right here. 1 over that would look like that, where the asymptote is there. The other one is just slightly, it's downward facing, And it's going through the x value of -3/4 right there. So if I was to draw the reciprocal of it, it's going to be positive on this side and negative on this side. For these, it's really a matter of factoring them. So this first one factored is x minus 4, x plus 3. So you're going to get asymptotes at x is equal to 4 and x is equal to -3. And the second one, when I factor it, I take out x squared minus 5x plus 6. And when I factor it, I get -2 minus 3. X minus 2 and x minus 3. And this one's an upward facing parabola. This one's a downward facing. So for the upward facing one, it's going to have, like I said, 1 at x is equal to -3 over here, 1 at x is equal to 4. And because it's an upward facing parabola, like that, wherever it's negative, the reciprocal is going to be negative. So it's going to look like that. To find the max point here, find the halfway point between -3 and +4, which I believe if you add them together, it's a half. So half x. So if you plug half x into this formula here, you'll find the y value. And then remember to put it 1 over that. So half here, -3.5 plus 3.5, 3.5 squared, it's going to be 1 over 3.5. This is going to be negative. This is going to be positive, so it's going to be a negative value. So whatever 3.5 squared is, and then find the reciprocal. So it's going to be at -0.008. And then the other sides of it are going to be up here in the positive zone. So it's going to follow the pattern of the parabola. Because the other one is facing downwards and going through the points 2 and 3, so it's going to be over on this side. Its inverse graph is going to look like that. Plug them into Desmos and you'll see. Very much what we did in the first 9 and 10. That's why I don't want to do it again. An equation in this form has a graph that closely matches the graph on the right. Okay, fair enough. Let's see if we can figure out the reciprocals, or sorry, the asymptotes from the graph. Well, it looks like this left asymptote is at x minus 1. And this right asymptote is at x equals 1. Yeah, they even write it right there. Looks like there's negative down here and positive right here. So that means the parabola is going to be coming down like this, going through there. It's going to be negative here. It's going to, its vertex is probably going to touch there, and then it's going to go back up. So if we look at that, and we say, okay, y is equal to k, and we know it's going to be a. We don't know if there's a stretch or not, but it's going to be x plus 1 and x minus 1. And we have a couple key points that we could plug in that are quite clear, right? So let's just make a copy of that. We just go back and see if we can see some clear points. It looks like there's a clear point right up here at 0, minus 3. See if there's any other clear points. Not really. Not really. But that 0 minus 3 will help. So that means when, for this, when y is minus 3, x is 0. Now we can't quite figure this part out yet. Let's forget about k for a second and focus on what the parabola would be. So the parabola is going to have a let's focus on this. Let us try it first. Because we have two variables, we need two x values. Yeah, k could be more than one. No, that's the problem. Yeah, I don't want to assume it. Let's just try it with what we have. I think they're assuming there's no stretch at a, because they gave us x squared plus bx plus c, but there could still be a factor. I think they're making us assume there's no a, and just assuming it's going to expand. So you get x squared minus 2, like that. So I think there's going to be no and that's when x is 0, right? So I think x, and this is all squared. Yeah, so I think what they're assuming is that there's no a there. And if I expand x plus 1 and x minus 1, I get x squared minus 1, like that. Which means you just have to figure out k, right? Like that. If I multiply both sides by x squared minus 1, I get minus 3x squared. Minus 3 times x squared minus 1. If I expand that, I get minus 3x squared plus 3 is equal to k. And remember that x is 0 in this case. Yeah, so let's go back here and remember that x is 0 in this case, and that x 0 squared would leave minus 1. If I multiply both sides by minus 1, I get plus 3, so k is equal to plus 3. So I think what they're trying to tell me that is the formula is y is equal to 3 over x squared minus 1. And that's where the 3 comes from. Let's see if that works. So let's try, first of all, x squared minus 1. And let's try g of x is equal to 1 over f of x. No, not quite. Oh yeah, sorry, it was 3, wasn't it? Yeah, it looks like we got it. Yeah. I don't know if we can test some of these values. I mean, this looks like minus 2 comma 1. Let's see if that exists on the graph. I think this is supposed to be close to 2 comma 1, and then maybe they just screwed it up. It's just below it. Personally, I think you need to have an a in here, and you would need to solve it all. But if you're just basing on what they've given you, you could assume that x plus 1, x minus 1 expands into that. Let's just see what g of minus 2 is. Yeah, it's exact at 1. I don't know if we got it or not. I don't know if there's any. You'd need a few more clean points. And really, that's the only clean point they give you. And there's the y value. And the only way you can reach 3, I think that's the best you can do. It doesn't quite match the graph there, though. Maybe there's a secret. You can check the back of the book, but I think that's what they were aiming for. Okay. So this is a situation where you have a decay curve, or actually it's not going to be a decay curve, it's going to be a, I'll show you what it's going to be in a second. So this will produce a graph. So this is kind of a weird question. Because normally for something dying it would be a decay curve. But in reality, 1 over t is the same as 1 over x. And 1 over x will produce a graph that's like this, where the right side is positive and the left side is negative. Now, because time is on the x-axis, it starts at 0 and moves that way, you can pretty much ignore the left side of the graph. So this is what they're talking about. In other words, the bacteria are going to start big and then decline and approach 0 but never reach it. The 1,000, once you figure this out, the 1,000 is like a vertical stretch. In other words, when time is 1, we're going to be at 1,000 here. 10,000 rather. And it's going to skyrocket just to the left of that. Just plug in 1 there for time and you'll see that it becomes 10,000. And anything to the left, it'll skyrocket. Anything to the right, it'll start hugging 0. So what about 20 seconds? Let's answer the questions one by one. You get 10,000 times 1 over 20. Take a 0 off both. Divide that by 2. Times a half is the same as divided by 2. So there will be 50 bacteria at t is equal to 20. Or 500 rather. Which means at the 10,000 point, it's going to decline quite a bit. But we will find the point 20, 500 on this graph. How many seconds? Well, only 5,000 bacteria left. Well, bacteria is on the y-axis. So you have to say 5,000 is equal to 10,000 times what? Value of t. Okay, let's multiply both sides by t. That gets rid of the t on the right side. Then we divide both sides by 5,000. Three zeros get canceled. 10 divided by 5 is 2. So at time is equal to 2, there's going to be 5,000, which makes sense because at time 1, there was 10,000. After how many seconds will only 1 bacteria be left? So that's the same thing. You do 1 is equal to 10,000 times 1 over t. Multiply both sides by t. Cancels that on the right. When time is 10,000 seconds, there will be 1 bacteria. This model is not always accurate. Determine what sort of inaccuracy this model might have. Assume that the solution was introduced at t is equal to 0. Based on the inaccuracy, what should the domain and range be? In other words, they're saying you can't include this part of the graph because there's no such thing as negative bacteria or negative time. So that's one inaccuracy. The other inaccuracy is there will always be some bacteria. But technically, we would kill some bacteria after a certain time. You'd kill them all. So that's the other inaccuracy. But I think what they're getting at, yeah, you should probably stop when there's 1 bacteria, which is 10,000 seconds. So that means you should probably restrict the domain to at least time is bigger than 0. And since there's a maximum of 10,000 seconds, 10,000 bacteria, that exists only when time is 1. Yeah, so that means time domain should actually be bigger or equal to 1 in this case, because there's 10,000 bacteria to start with, and that exists at time 1. And technically, it should probably be time smaller or equal to like 20 or 10,000, because you're not going to just have 1 bacteria left. But this last part is debatable. I would say that is definitely the restriction, which means that y, or bacteria, will always be smaller or equal to 10,000. Let's check this out on the graph, see what it looks like. Another way to write this is like this. To see your scale, you have to get up to 10,000. So you should probably make your y from 0 to 10,000. And if you really want to see it, make it 11,000. Sure enough, you'll discover the point 1, 10,000 somewhere in here if you get a steady hand. And since we start with the bacteria, we should put a domain restriction. Since we start with bacteria at 10,000, that should be our domain restriction, which creates our range restriction. And we can answer all those questions. That's the bacteria at 1 second. That's the bacteria at 2 seconds. That's the bacteria at 20 seconds. And as we proven, there's one bacteria at 10,000 seconds. Use your graphing calculator to explore and describe the key characteristics of the family reciprocal function x plus something. Yeah, that's not as interesting as other things. But yeah, whenever you're adding something like that, that's an x translation to the left. So I'll show you. Get rid of that. So if you do this, you can actually let Desmos show it to you. And just make an n slider and make your n go as far as -100 and as big as 100. And just use steps of 1 and just click play. So I'm going to click home. And yeah, we should actually click quit. There we go. So as it gets -n, it's translating to the right. As it gets +n, it's translating to the left, which is what you would expect with an x translation. Because you're adding something to x, it's doing the opposite. So you could state the, if you stop it anywhere, let's say -5, right? Here is the x is equal to +5. So you could state the restriction on the domain as x cannot be n. Or you can state the asymptote as x is equal to n. And see, it'll do it for you. Oh, actually it'll be x is equal to -n because it's the opposite. So you can see we can now have an asymptote follow us around. Why -n? Because the translation is the opposite of what n is. For x transformations, it's the opposite of what you would expect. So you could say that, okay, xer, yer, but x cannot be -n. If that's what they're asking. And the domain is xer, but x cannot be -n. Yer, but y cannot be 0. Well, when y-intercepts occur when x is 0. So when x is 0, the y-intercept will always be 1 over, I believe, hang on, let's see if I can set this up. It's going to always be 0, comma, will be -1 over n. Let's see. Hard to see on that one. Let's bring that closer to 0 to get an idea. No, it's just going to be 1 over n. There we go. That'll give us a better idea. So let's just make our n go up and down by 1. We'll hit play. And you'll see it's drawing my y-intercept for me. And I should label it. There we go. Notice it's drawing two. Sometimes it's, yeah, it's only ever going to be 1 because it's only one spot, part of the graph where the y-intercept can exist. And there will be no y-intercept when n is 0. And it wasn't the opposite because y translations or y values don't have any opposite values. If graphed, compare it to the line. That's a good question. So let's do a g of x that is the same as the line. So they're always going to intersect when y is 1 and when y is -1. That's because 1 over 1 is still 1 and 1 over -1 is still -1. And where the line's x-intercept is where the asymptote of the parabola is. I should probably make this a different color. There we go. Anyway, it's worth exploring these things because it's easier visually. To the baseball tournament, your friend missed a class. Write a concise explanation of the steps needed to graph a reciprocal function. Nah. Sketch each of the following. So these are exceptions to the rules. So it helps to understand each in order to sketch them. And then there's another final one here, so we'll do it. And I'll just stop this. Stop the madness. Okay. Okay. I'm going to skip all that, and we're just going to focus on this. And this I'll do in a bit. First of all, understand the graph square root of x. The square root of x has a domain that's restricted to the right and a range that's restricted there. So x is bigger or equal to 0 and y is bigger or equal to 0, which means if I take the reciprocal of y, first of all, it can't exist here because y is 0 there. So you're going to see this weird thing happen like this. And they'll probably share a spot right here at 1, 1 because y is equal to the square root of x. When x is 1, y is 1, and 1 over 1 is 1. So I think that's what you're going to see. Yeah. And they share the spot 1 over 1, 1. Okay, what's next? What's a cubic look like? Just ask yourself, what's the parent function look like? Right? Cubic has a similar pattern to like that. The only difference between it and a parabola is it goes negative. So that means, since this is negative, and that's 0, 0, so we're going to have an asymptote right there on the y-axis for the reciprocal. It's going to be negative here. So as y values go huge, 1 over them will go small. So we're going to see something like this. So it's going to look a lot like a regular 1 over x, and that's because 1 over x, which is a power of 1, and 1 over x3 will have similar reciprocal situations. Same with 1 over x to the 5. But 1 over x squared will create this weird thing. 1 over x squared is one of the few times where you'll see, because 1 over x squared is like this, I think. And so the reciprocal will look a lot like that. And we'll see. They don't have it here. Let's try 1 over x cubed. Oh, just x cubed is the parent function. Yeah, so if you look at the green, I got it right. I didn't get the hugging correct, but the asymptotes are correct. It's just distorted because it's cubed. And here's the relationship to the other one. Okay. And now, what about this one? Well, 2 to the x, try to understand a growth curve's domain and range. A growth curve will start way over here in red, never touch the y, and go up. So that means all this is positive, which means 1 over it will be positive. These are small values of y. These are big values of x. And by the way, it goes on forever like this. So there's not going to be an asymptote because all values of 2 to the x are positive. So that means 1 over it will also exist. Since these are huge y values, expect to 1 over it. Expect the reciprocal to look a little bit like this. A little bit like a decay curve. And they'll probably share this point, and this point is always base, comma, or 0, comma 1. So they'll probably share the point 0, comma 1, and that's because the 1 over 1 is 1. Let's see if that's true. So let's turn this off. Here is your standard growth curve. Zero comma 1, and here's the reciprocal. Look at that. Looks almost exactly like the decay curve. As a matter of fact, we should look at the decay curve to see if it's identical. Look at that. The reciprocal of a growth curve is a decay curve, which actually makes total sense because 1 over 2 to the x let's see if I can explain it in a way that works. This is the same as, so g of the x there is the same as this. So that's also the same. And I don't know. I think it's because this as a transformation is the same as this. So it just happens to be the same curve because the transformations end up being the same. So this is a reflection in the y-axis, and this just is a standard decay curve. I don't know if I can accurately explain why they're all the same. I think their reflections just happen to match. And what about the last one? 1 over sine x. That's going to be interesting, actually, because I don't think you're going to see it. I think you're going to see a sine curve in the 1 over the sine curve. So a sine curve has an interesting thing that half of it's positive and half of it's negative. The maximum value it reaches in y is 1, and then gets very small. So I suspect possibly it'll do something like this. And of course, 1 over sine x is the same as secant x. And that's exactly what a secant graph looks like. So let's have a look. Yep. And let's have a look at a secant. Oh. But out of phase by 90 degrees because we've essentially inverted it instead of making complementary, so if I want to match it, I believe it's by 90. Almost. It's not quite. So it's 45. Let's try 45. Not quite, still didn't get it. Interesting. I'll have to figure that out. Why is it phase shifted? An inaccurate phase shift. I'll figure out the phase shift. But anyway, it looks a lot like a secant curve. It should be the exact secant curve, though, because secant is the same as... Oh, sorry, cosecant. What am I thinking? There we go. Same curve, because cosecant is 1 over sine x. Alright, and determine the equation of function shown here. Okay. Looks like we have an asymptote of x minus 4. I don't see any clear dots, but I'm sure there's some clear dots in there somewhere. Right there. Minus 3 comma 0. So we're talking about x plus 4 is the line. 1 over x plus 4. But to make sure, so it's 1 over x plus 4 should be the line. But just to make sure, k, we know that y goes through minus 3 when x is minus 3. Y is 0. Yeah, it's just k is 0, or k is 1, yeah. So the whole thing is lowered by 1, because it looks like the new horizontal asymptote is this. So I'm going to suggest that it's this. 1 over x plus 4 minus 1. Let's see it. We put in all our stuff. And we'll make that these green. And that looks pretty close. Yeah, minus 3 comma 0, which is on that graph. And that's because we have 1 over x that's been, the entire graph has been lowered, so the translation is accurate. And I figured that out by figuring out where the horizontal asymptote was and where the vertical one was, and then just using my understanding of line curve. So there you go. End of story.